You are here because you know him very well and his research very well, but just to touch on that a few minutes. His real research interests are in methodology, particularly in linear models, multi-level models, and especially process analysis, and that's the reason that we are here today. What is very interesting about his work is that he made this type of analysis accessible to a lot of researchers in different disciplines. And you'll see some exposure to that today. He's very productive, he's very active, he's co-author or author of 3 different books, and one of them is coming out in the next few months. And if you look at his webpage, you'll see that he'll be traveling a lot, and we're grateful that he made time for us to come visit us in Montreal. Without any further introduction, I'll leave the floor to Dr. Hayes.
Thank you for the invitation. I've been to Montreal a few times in the past. Today I'm going to give you a very, very broad and very, very fast overview of the integration of mediation and moderation analysis. Now, this will require about 2/3 of my time to be dedicated to the fundamentals. So it really isn't until the last half hour or so, as I start to run out of time, where things get really most exciting. But we do have to spend some time going over some of the fundamentals, and along the way, you're going to be introduced to a statistical tool that I've created that makes some of this work that I'm going to do, that you're going to be doing very, very, very easy. So you'll get an introduction to that, and those of you who will be around after lunch for my workshop will get lots of hands-on experience working with this tool. So here's where we're going. We're going to talk about mediation analysis. I'm going to give you a fairly modern orientation to mediation analysis. Things have changed a lot since 1986, when people first started thinking and citing the literature in mediation analysis most frequently. Then you're going to get a overview of the fundamentals of moderation analysis. And then I'm going to combine them together. That's where things are going to get most exciting toward the end. I'm going to integrate them into this procedure that I've called conditional process modeling. That's not a term that you have probably heard before. That's because I made it up. But it's something that I think that you will hear more about in the years that follow. And again, I'm going to describe a tool that I've invented for making all this very, very easy to do in software that you no doubt are already using. For today, I'm going to be relying on data provided to me by a gentleman at the business school. I believe he's at, I don't want to get this wrong on camera, but I think it's the University of Richmond, and Jeff Pollock. So these data, although the article was published recently, are several years old at this point and come from a time in which the U.S. economy was really in pretty bad shape, at least in terms of recent history. Things are improving quite a bit now, in spite of Congress's attempt to thwart our progress. Things are getting better, but the context of this is a bad economy. And we've got data from a number of people who are entrepreneurs. These are generally business owners trying to make their way in this economy. These entrepreneurs are all members of a social networking site, a networking site that's focused primarily on small business. So small business networking site. And they're asked a series of questions relating to how much stress they feel with respect to the economic climate that they're in, how it's affecting their business. They're also asked a series of questions tapping into their business-related depressive affect. So how down are you feeling? How hopeless are you? How concerned are you about your well-being with respect to your business? The primary outcome of interest we're going to use is this thing called withdraw, intentions to withdraw from entrepreneurship. So this taps into people's sort of projections as to whether they feel like maybe they're going to get out of this. They're just going to go and do something else instead of trying to weather a difficult economy. And then we have a measure of business-related social network size. So participants in this study were asked a series of questions to tap into how deep or rich their social ties are in this social networking site. Primarily, it's a measure of how many contacts they have on a day-to-day basis regarding their business or business-related matters. So these are the 4 variables that we're going to focus on primarily. There are a couple of control variables that I will mention in a sec. But this is where we're headed. We're headed toward this model. This is a model which contains both a moderation and a mediation component, something I call a conditional process model. And this is a conceptual model. When you see boxes and arrows, you start thinking about path analysis and structural equation modeling. And that's not what this is representing in a formal sense. This is a conceptual model. It outlines a process in visual terms. But as we'll see when we go into actually estimating this model, it'll look different. What I call the statistical model. So here's our question. Does depressed business-related affect function as a mechanism through which business-related economic stress influences an entrepreneur's intention to withdraw from entrepreneurship? That's a mouthful. Is the strength of this mechanism contingent on the extent to which one feels interpersonally connected to a network of peers in the business community? So what we'll do with this model is we will break it up into its parts. There's what we call a mediation component, which is this triangle. There's a moderation component, which is here. And when you tie them together, you have something called a conditional process model, where we can model the contingent nature of mechanisms. So let's start with mediation. So a mediation model is a model in which we are linking some kind of putative cause, something we believe is a causal agent of influence on some outcome, presumed outcome variable y, and that influence of cause on effect occurs at least in part through some kind of an intermediary variable m. Now those intermediary variables, or what are sometimes called mediators, could be anything. It could be a psychological state of some kind. It could be some kind of a cognitive process. It could be a biological response to something. It could be emotional. It could be anything. It's the thing that we conceive of as the mechanism through which X is influencing Y. In effect, it's an attempt to answer the how question. How is X influencing Y? Well, it's occurring through this mechanism. This mechanism being this, what we call an indirect pathway from X to Y. So M, this intermediary, or what is called a mediator, is something that has to be thought of as causally located between X and Y. In other words, it's the middle variable in a chain of causal events. X causes M, and that influence on M then goes on and transmits effect to Y. I say this because now and then I'll get questions from people about mediation analysis, and when you probe them further, you realize that their M is not between X and Y. So it's somewhere else out in some conceptual space. And that's not a mediation process if we can't make this assumption, at least, that M is causally between X and Y. Now, these are causal models. They're going to carry with them all the standard criteria that we use for making cause-effect claims. And we know these are often very often. They're actually typically fairly difficult to meet these conditions. Covariation. But it turns out covariation is not a condition of causality, even though we often teach it that way. Generally thought of as covariation as one of those criteria, the other being temporal precedent. Cause has to precede effect, and then the third being you ruled out alternative explanations for the association. Now, often we don't have the ability to meet those conditions in the data we have. Sometimes it's only our theory. That may be the strongest thing we've got to hang our causal claims on. That's okay. If that's the best you've got, if you can make the argument, and you can make the argument convincingly, well, that's sort of what science is about. It's partly that making that argument. This is important because I get questions from people all the time who have data that are purely correlational in nature, which this example I'm going to be using is purely a correlational study. And they want to know, well, can I do this stuff? Can I do this kind of analysis? They're looking for permission, I think. And the answer is yes, of course. I mean, we shouldn't limit ourselves. We shouldn't limit the mathematical tools that we can bring to understanding our data just because we can't meet certain conditions that we would prefer to meet if we could for making these kinds of claims. So as long as we recognize the limitations of our data, we can do anything that we want to with it mathematically that helps us to better understand it. So as long as we recognize the limitations of our data and couch our interpretations with the appropriate caveats and claims. I like to say that inferences are products of mind, not math. Right? The inferences are up here. They're not in the mathematics. They're what we do with the information mathematics gives us. Math doesn't care. Doesn't even know where the data come from, anything about the design. Okay, so our inferences will always be design bound to some extent. But the inferences are up here. They're not in the math. Okay, this is a simple model. It's a simple mediation model that we're going to talk about. That's not to say, however, that it's trivial, even though maybe it's an oversimplification of most complex processes. This is not at all uncommon. You see these kinds of analyses being done all the time, and here are a few. These are just screenshots of figures in various journals in the marketing area. These are in abundance. It's not difficult to find these. I've got a catalog of hundreds of these images. Here are a few from social psych. Social psychologists love this stuff. Love it. That's my background. And social psychologists are doing this stuff all the time. Content analyses of the social psychology literature show that you really can't read a typical issue of a social psych journal like the Journal of Personality and Social Psychology without encountering at least a couple of these. And in fact, I just did a content analysis of psychological science, which is a broad journal for the entire discipline of psychology. And every single issue over a 2-year period had at least one of these kinds of analyses in it, and typically more, as many as 7 in one issue that I found. I don't know if there's any people from the health area in the room now. Usually I have a few, unless the whole room, if I'm giving to a health audience. And this is common in health as well. People who study public health, people who study health communication, health psychology. These are all over the place. It's worth learning a little bit about them. People are doing this all the time, and no doubt you will as well. I want to spend some time going over some of the mechanics of path analysis. This is important because when we get to the end where we start integrating mediation and moderation, we're going to have to play around with regression coefficients that are estimated in a variety of ways. So a very rudimentary primer right now on path analysis. So here's our simple mediation model, and up here I've placed an even simpler model without a mediator in it at all. So we have 3 variables. We want to quantify one variable's effect on another. Now again, remember, I'm going to condition that claim of effect always on the quality of my data and my research design. I'll use the term effect here, maybe when it's not technically warranted, but you get the idea. In the end, the claims we make are going to be based on design, not on mathematics. So I'll use the word effect, but I'll use the word effect loosely. So we want to quantify the effect of one variable on another. We can do that in a lot of different ways. I think regression analysis is a very, very simple and general way of thinking about quantifying effects. And everything that I'm going to talk about today applies to OLS regression. And mostly applies when you do this kind of analysis with continuous outcomes in a maximum likelihood-based framework. I'm going to speak in OLS terms, but this is generally true in structural equation modeling. As long as we have an M and a Y that are treated as continuous, it doesn't matter if they actually are. You're just going to be analyzing them as if they are. So let's say we want to quantify X's effect on Y. Well, let's just regress Y on X. That regression coefficient, and I'm just speaking on standardized metrics here. That's the metric I prefer, but this applies to standardized metrics as well. The unstandardized regression coefficient is C. That quantifies X's effect on Y, numerically. More formally, it tells us how much 2 cases that differ by 1 unit on X are estimated to differ on Y. So that regression coefficient we'll just call C. Now imagine, here's the equation for that simple regression model. Right? We're just estimating Y from an intercept plus X, which is getting some weight. let's do the same thing for m. Regress m on x, you get then a regression coefficient a, which estimates how much two cases that differ by a unit on x are estimated to differ on m. There, that's the second equation. Then the third equation, we're going to estimate y from both x and m. That'll give us two regression coefficients, one for x and one for m, which I've labeled b and c prime. So b estimates the amount by which two cases that differ by one unit on m but that are equal on x are estimated to differ on y. C prime has the reverse interpretation, reversing the roles of x and m. How much two cases that differ by one unit on x that are equal on m are estimated to differ on y. So imagine these three regression coefficients. That gives us these four regression coefficients. It turns out that there's a relationship between these regression coefficients expressed here. C, which we call the total effect of x on y, cleanly partitions into two components. The direct effect of x on y, which is c prime, plus the indirect effect of x on y through m, which is the product of a and b. So that's this equation here. So the total effect of x on y is c. C prime is the direct effect of x on y, and the product of a and b is the indirect effect of x on y through m. A little algebra shows you the indirect effect could be thought of as the difference between the total and the direct effect. And those of you who have done mediation analysis know that people sometimes make a big deal of how much an effect changes when you introduce a mediator, and that's sort of reflected here in that difference. That's just the indirect effect, though. Okay, so this relationship between the direct, total, and indirect effect applies to any data you can give to an OLS program. It doesn't make any difference. That will always be true. As long as you're treating m and y as continua, this relationship will hold. You can't make that. You can't give me an example where that wouldn't be true, because it will always be true. It's not very often that I'm comfortable speaking in absolutes, but this is one which I am. Now, when we do research, and often we're doing research with data that don't lend themselves to unequivocal causal interpretation, we have to deal with confounders. Right? Relationships can exist for a number of reasons, among them being that they have all kinds of maybe shared influences, shared causes. It's nice to get rid of those statistically. And what I want to show you here is that this relationship holds even after you account for those confounding variables. So all I've done here is I've taken my model and I've added, here I've only added one, but you could have many of these confounding variables added to these models and the same will be true. So all I've done is I've added on a confounder, a potential confounder variable into each of these equations. We give them some weight. We let an OLS regression program figure out how to weight these things to produce the best fitting model. And this equation still holds. So long as you partial these potential confounders out of both y and m. The example we'll use today does include three potential confounding variables. Okay, if you don't want to take my word for it, let me illustrate. So here I'm predicting our entrepreneurs' reported feelings of economic stress on their withdrawal intentions. These are all scaled such that higher values represent more. So higher stress, higher withdrawal intentions, and so forth. I've also got three variables that I'm partialing out. The sex of the entrepreneur, their tenure, which is essentially how long they've been in this business. And then ESE is entrepreneurial self-efficacy. So when we regress withdrawal intentions on economic stress, we get C of 0.019. I don't know if you can see that in the green, but there it is. And that comes from this regression where I'm predicting withdrawal intentions from economic stress plus these confounders. Here's an SPSS command that generates that output using these data. So that's the total effect of economic stress on withdrawal intentions, holding constant sex, tenure, and entrepreneurial self-efficacy. We do the same thing estimating depressed affect from economic stress, as well as the potential confounders, and we get 0.159 as our regression coefficient A. one more regression predicting withdrawal intentions from all 5 of these variables gives us B of 0.707. So when we put all these together, I apologize, first the direct effect as well, we get C prime, which comes out of that same model, right? Same model, different coefficient gives us that direct effect. So here it all is together. So our direct effect, C prime, our indirect effect is the product of A and B, and then our total effect is C. And what you can see, the whole point of this is to show you what I wasn't lying to you before. That works. The total effect is perfectly partitioning into those 2 components, the direct effect of X and the indirect effect of X. So what does this all mean? How do we interpret this? Well, here's a generic way of thinking about direct, indirect, and total effects first, and then I'll give you a more specific interpretation relative to these findings. So we can say that 2 people who differ by 1 unit on X are estimated to differ by total effect units on Y on average. So that's C. They differ by indirect effect units on average as a result of the effect of X on M, which in turn affects Y. And then there's something that's going to be left over, and that's the direct effect. The rest of that difference, the difference of direct effect units, is due to the effect of X on Y that's independent of M. So substitute in our variables into this generic interpretation, and you get this. 2 entrepreneurs who differ by 1 unit in their economic stress. That's 1 unit on whatever the metric is being used to measure their stress. But they're of the same sex, tenure, and entrepreneurial self-efficacy, because we're holding those constant. We're parceling those out in the model. They're estimated to differ by 0.019 units of withdrawal intentions, again, in whatever metric of withdrawal intentions we've used. The person with 1 unit more stress is estimated to be 0.113 units higher in withdrawal intentions as a result of the positive effect of stress on depressed affect, which in turn affects withdrawal intentions. So that 0.113 units due to stress putatively influencing depression, which in turn putatively influences withdrawal intentions. And then holding depressed affect, tenure, sex, and entrepreneurial self-efficacy constant, an entrepreneur 1 unit higher in stress is estimated to be 0.094 units lower in withdrawal intentions, lower because the direct effect is negative. Higher X paired with lower Y, holding M constant. So let's shift to inference. We have 2 effects that primarily are of interest to us, although some people care about the total effect. Focus on the total effect in 21st century mediation analysis is not as common relative to the 20th century. So there are primarily 2 effects that we care about: the direct effect and the indirect effect. We can get the total effect from the 2 of those. So inference focuses on, can we make anything out of this in a statistical sense, right? We need to deal with alternative explanations. Statistical control can help us some. But the most parsimonious of all alternative explanations for a relationship is chance. Right? So that's primarily what we're doing when we deal with inference. How plausible is chance as an explanation for this obtained result? Now, if you're a confidence interval advocate, you know chance is not necessarily something we focus that much on. We care more about just some inference about where in the realm of possibilities the effect resides, rather than whether 0 is among those possibilities. Either way, whether you're a confidence interval advocate or a hypothesis testing advocate, inference about the direct effect is for the most part not controversial. And we get an inferential test from any regression analysis. Any regression program that we do will give that to us. So here's our direct effect of minus 0.094, and we see from our standard regression table here that our p-value attached to that is 0.077, or a confidence interval which straddles 0. So if we want to take the 0.05 criterion seriously and literally, we would say, well, that's no evidence of an effect of stress on withdrawal intentions after you account for differences between these entrepreneurs and how depressed they are. Again, nothing controversial about that, nor is there anything particularly interesting about it either. Where things get fun, from my perspective at least, is dealing with the indirect effect, because that's where the most controversy is. That's where the most literature in statistical mediation analysis has been over the last 10 years, 15 years or so. The indirect effect is estimating the influence of x on y through this mechanism that's represented by the causal sequence, x to m to y. 21st century mediation analysis is going to base a claim of mediation on evidence that the indirect effect is different from zero. So we can quantify that indirect effect. I showed you how to do it. It's this product of these two coefficients. Well, there is a popular sort of 20th century approach to inference, and that's called the Sobel test, which says pretty much a standard inferential procedure. Let's take an estimate of our effect. Let's divide it by the standard error. And there are a variety of standard error estimators that are out there in the literature, primarily based on what happens with this third term. And that ratio, we have used the letter z because we are using the normal distribution as a representation of this sampling distribution. That is, we invoke the assumption that this sampling distribution is normal under the null hypothesis. And with that ratio, we can calculate p-value. Tag the p-value onto the obtained estimate. So standard approach. There's nothing particularly insightful about that you can learn from this, but all this information is available in any regression program. We've got estimates of regression coefficients that we either square or don't. We've got standard errors of those regression coefficients, which we square, and we take some square roots. Nothing terribly fun about doing this computation by hand, but not difficult, and it's available to you in any regression analysis that you've got. So you could plug away and get something, and what this shows us is that that indirect effect that we've calculated is statistically significant, that it's different from zero. But this test has serious problems, and I don't recommend using this. The problem with the Sobel test is that we're making this assumption of normality of the sampling distribution of the product of A and B. That is, that assumption is what gives rise to the use of the standard normal distribution for generating the p-value. Not a bad assumption to make in big samples, although even then you could make the case that that assumption of normality actually tends not to be true. It's not as bad of a violation in big samples, but in small to moderate samples, it's just flat out false. We know that the product of two random normal variables is itself not normal. We know that. Analytically, it can be shown that that's the case, and it's easy enough to show that through simulation as well. So the problem is the normal distribution is not an appropriate reference distribution for generating probability. So, and as a result of this, in part as a result of this, the Sobel test is among the lowest in power of methods for detecting indirect effects. So experts in this area are not recommending using this test, although it does remain popular. You'll see people doing it all the time still. I think eventually researchers are going to get the message, and I see that evidence of that happening already. People have talked about it before me, but some work that I've done with a colleague of mine at Vanderbilt, Chris Preacher, has helped to make this a little bit more popular, because it's a little bit easier to do than it used to be. So the bootstrap confidence interval is what I'm recommending these days. Now there is some literature that's coming out, or is out or coming out, which is showing that this can be improved upon. So it may be that in 10 years we're doing something different. But right now, this is what people are doing based on advice that's being given by people like me and others. Bootstrapping as an inferential method has been around for quite some time. But this is a place where it seems particularly well suited, because we're dealing with a situation in which the sampling distribution of a product, this product of A and B, it has a fairly irregular shape. That shape has been analytically derived, and it's relatively difficult to work with mathematically. This is a good situation in which bootstrapping is great, because bootstrapping is what we call a resampling method, which allows us to make inferences based on a sort of what we could call an empirical approximation of the unknown sampling distribution. And I say empirical because we're going to actually generate a representation of this sampling distribution through repeated sampling of the data. So here's how this works. We have a sample of, we'll call that sample of size n. That's our original data set, size n. So rows in a data file. So let's take a random sample of our sample. But we'll take a random sample of size n. So we're going to create a new sample from our original sample that is of the same size. And we can do that without being silly about it because we're doing this with replacement. So when we build a new data set from our original data set, sampling with replacement, if we draw a particular row from the data file as we're building a new sample, we put that row back in to be redrawn. If we didn't do that, obviously each time you do this, you'll get just the same data set. So you have to do this with replacement. So we'll take a random sample of the original sample size n, sample with replacement, and then we'll just say, well, this is our new data set, and we'll calculate the indirect effect in that new data set. And we'll do this over and over again, sampling with size n with replacement from the original data set, calculating the indirect effect in that new, what's called a bootstrap sample. Repeat this many, many times. I recommend at least 5,000. So after this, imagine you've got 5,000 of these estimates of the indirect effect. Well, think of this as a data set, 5,000 rows. There's a distribution there. You could imagine visualizing it with a histogram or something like that. That's an empirical representation of the sampling distribution of the indirect effect when sampling from the original population. So we use that distribution of the indirect effect over multiple resamples, multiple bootstrap estimates, as an approximation of the sampling distribution of the indirect effect from the original data. With this distribution, then we can generate an empirical estimate of we can generate an empirical confidence interval for the indirect effect. Let's just imagine sorting these from low to high, throw out the lower and the upper 2.5%, take the two endpoints, now the lowest and the highest in that distribution, those are the endpoints of a 95% confidence. It makes no difference what the shape of the distribution is. It doesn't matter what's happening in the tails or what it looks like in the center because you're only basing your inference on those two endpoints after throwing out the extreme 2.5% of the data on each side. There are variations on this. That's what's called a percentile approach to calculating a bootstrap confidence interval. There are things you could do, something called bias correction or bias correction and acceleration, which in theory should be better, although in practice turns out not necessarily to be, or at least not always. Now, it seems like a difficult thing to do, and obviously requires a computer. It's not something you're going to do pointing and clicking or whatever you want 10,000 times. But it's a perfect task for a computer. That's what computers are good at. So here's an empirical representation of the sampling distribution of the indirect effect in this model. I actually did 10,000 of them. So 10,000 bootstrap estimates of the indirect effect. Here is a representation of that sampling distribution. This is those 10,000 bootstrap estimates. We throw out the lower and the upper 2.5%. The two values that are on the lower and the bottom and the top then are 0.056 and 0.17. So those are the endpoints of a 95% confidence interval for the indirect effect. And because 0 is not in that interval, we use that as evidence that the indirect effect is different from 0 with 95% confidence. Sort of like saying p less than 0.05, although not technically that, because hypothesis testing is conditioned on a true null hypothesis, whereas this is not. I always get questions, and I'm happy to take questions later about the rationale for this. Is this cheating? Are we making up data? No. But it's worth spending some time talking about those issues toward the end, if you care to ask me about it. Okay, so do you need special programming skills to do this? Well, that would help. I have some programming skills, but I wouldn't want to be doing this each time I have a data set to analyze. How many of you recognize this? You've got to be probably around my age or older to recognize this. What is this? Basic, yes. Can you be more specific?
Recollection is difficult.
Well, I remember this very well. This is the screen that comes on when you turn on the Commodore VIC20. Right? This was a big deal in the 80s when I was in high school. I think it came out in 1982. And this was really the first computer that was available to people at a reasonably good price. This machine is sort of credited in part for bringing personal computing into the home. You could say that maybe Apple stake claim to that as well. So my father bought me one of these when I was young, and I love this thing. I spent so much time on this, and I learned to program on this machine. I would lock myself in my room and I taught myself BASIC there. Mom, how would you come out for dinner? My first publication actually was when I was 14. This was a magazine that supported this Commodore computing platform, and I published a number of things over the years. In that, this particular cover actually it shows my thing on the screen. You can't really see it, but I wrote like a math learning utility for the VIC20. So I've been programming and publishing since early high school, and that's why I learned to program. And I credit my father in many ways for where I've ended up in that sense, because I think it's really sort of influenced where I went. I've spent a lot of time in the last 10 years writing software, you might call them add-ons for existing software, to make data analysis modern methods a little bit easier for people. So we were talking about the bootstrap confidence interval and how it requires a lot of, it would require some kind of computer programming skill, but that's what programmers do. You as a user don't have to think about that if you've got the software that does it. And so I've spent some time with a colleague of mine, Chris Preacher, writing about mediation analysis, and in particular describing some of the principles I've just gone through and others, but providing as well computational aids that make it easy for people to do. And before 2012, these are the types of procedures you might be using. We published something in 2004 with this test. It's really badly named, called Sobel, that does some of this bootstrap stuff in simple models like I've just described. We did a follow-up paper to this in 2008 for more complex models with this macro called Indirect. These are both available for SPSS and SAS, and you'll get some experience using these, those of you who are hanging around with me later today and tomorrow. They're fairly easy to use. And in fact, for SPSS, they're actually, you can integrate them right into the SPSS window, so it's point and click. Not difficult at all. These are pretty much obsolete now because I just released last year, the beginning of last year, a new tool. I've been writing tools like this for mediation and moderation analysis for the last 7 or 8 years. And then when I started teaching this more formally at Ohio State and elsewhere, realized, boy, it's kind of tough to keep track which tool does what. And so I thought, well, I took sabbatical a couple years ago and thought, well, one thing I'm going to do in the sabbatical is I'm going to write a new tool that sort of does everything that all my other tools do, just all sort of in one nice package. And so that's what Process is. So it does the kind of analysis I just described and a whole lot more. So it combines all these features of some other macros that I've written over the years. I didn't know how this would be received. I liked it, and it made teaching a lot easier. People seem to enjoy this, though. I've heard people call it addictive. And it is in some ways. I have a colleague of mine down the hall says, I didn't get much sleep last night. I was using Process, and I was looking at my data in all these different ways, and it was so easy to do that with this tool. Things that normally are difficult because you got to write the code or do all kinds of juggling of data file around in various ways, Process makes it pretty easy. Anyway, this is freely available. You can find it from my homepage. So here is an example of processed output. Can you see this in the back? Some of these are, you okay? Okay, so this is, I know some of the text is a little bit light. So here is a simple mediation analysis in Process. So here's our conceptual model. And this is the statistical model. Now in mediation analysis, the statistical and the conceptual model are nearly identical. When we do moderation analysis, you'll see there's a big difference between the statistical and the conceptual model. So this is the model that we're going to estimate, and this is a more formal path diagram. You can see I've got these errors and the kinds of things you see if you were drawing like a structural equation modeling program like AMUS or M+ or other things. Process can be used as syntax, and here is the code in SPSS that would generate this analysis. So I have a version for SPSS, I have a version for SAS as well down here. You'll learn about this after lunch today, how all this works and what all this means. The point is that it's just a simple command that you would type into SPSS syntax, and once you've defined process, it will do this analysis. The SPSS version does have a dialog box, so you could install it with any luck and access to the machine. You could actually integrate this right into the SPSS menus, which makes it a little bit easier, and I know a lot of people like that. So what I'm passing around for you is output from process. And I don't want to spend lots of time dwelling on this. We'll go over this after lunch, and for those of you who won't be with me, I think you'll find this fairly straightforward and simple to interpret. Well, what you'll see is the string of output, and this is only part of it. So this is the first page, the second page of the handout. And what we see is that the process was automatically doing all these regressions. So here's our model of depressed affect, which includes all these predictors, and there's our A coefficient, that A path. Then it's automatically doing the second regression. So that's withdrawal intentions, and there are the predictors, and so there's B and C prime there. And then because I requested it with an option, we get this thing called the total effect model, and that gives us the sum of the direct and the indirect effect. So that's what we call C, total effect. Here's where all the fun is. This is a summary where we get the total effect of X on Y. There's that 0.019 I showed you earlier, the sum of the direct and the indirect effect. There's the direct effect. And then the indirect effect, and here we see, because I asked for it, a bootstrap confidence interval. This is the lower and upper bound on the 95% confidence. And that doesn't straddle 0. It generates the product force. Right, so that's our indirect effect, A times B. There's the confidence interval. It even generates an estimate of standard error, but it does that through bootstrapping rather than through something like the Sobel test formula. Okay. I failed to mention to you that I don't know if this was obvious to you. Let me go back to the beginning. I say this because I'm going to skip a couple of things, but I want you to know that these slides are all available, and they're actually there right now. So if you have a computer with a wireless connection, you can actually download all these slides. I say that because I'm going to skip some things. I don't want you to feel like you're being cheated. It's there. You can see it. You can download it. It's simply my webpage, which is easy enough, /public, and then /concordia.pdf. That should download if you point your browser or your iPad or whatever to it right now. So I'm going to skip this for now. We can come back to it if you want to later, because I want to get into moderation. Sounds like mediation, looks different, conceptually very, very different, and statistically totally different. So even though the two words are similar and often used interchangeably, they are very, very different. They shouldn't be interchanged. They're very, very different. So we talk about some variable's effect on Y. So X's effect on Y is moderated, not mediated, moderated, if its size or direction is dependent on some third variable. Could be more than one variable, but in this case, I'm talking about a single variable, and I'm going to use M here. Not to confuse you, we were using M as mediator. I'm using it as moderator here. In context, it determines whether it's a mediator or moderator. We're now talking about moderation, not mediation. So this moderation refers to the conditions that facilitate or inhibit an effect, enhance, or it talks about questions of whom. So for whom is this effect, large versus small, present versus absent? So here's a graphical or conceptual depiction of mediation, where x's effect on y is itself influenced by something else. Hence the arrow from M pointing at the path from x to y. So M is depicted in here to moderate the size of the effect of x on y. So that effect depends on M. And in that case, we would say that M is a moderator of the x-y relationship. We also use the term interact. It's this interaction and moderation of the same thing, different terms for the same thing. X we call the focal predictor and M the moderator. It's nice to use those terms because when we talk about these models, it's nice to think, well, what is the causal agent you're interested in? That's the focal predictor, and which is the moderator? It's a very, very quick overview of one property of partial regression coefficients, and that's that they are unconditional effects. So let's consider a simple regression model like this, where we've got only two predictors, x and m. So here's an arbitrary example, just pulled some coefficients out of a hat. And so here's a model of y from two variables, x and m. Here is some various values of x and m, and values of y that that model generates. Here's a graphical depiction of that model. So x on the x-axis, y here, and then various values of m. And thus the lines depict what y hat is from those various combinations of x and m. The thing to point out here is that regardless of which value of m we choose, a 1 unit difference in x is associated with the same expected difference in y. So 1 unit meaning a distance of 1 unit on x. Regardless of which value of m you choose, the difference in y is the same between those two values that differ by 1 unit on x. It makes no difference what value of m you choose. That, in other words, these are parallel. That's the property of parallelism. It doesn't make any difference which line you pick as you move from left to right. You change by the same amount on the y-axis. In this case, B1 is the coefficient for x, or 0.1. As you change x by 1 unit, y hat increases by 0.1 units, regardless of which value of m you choose. So we would say x's effect is independent of m. It doesn't matter which value of m. So B1 is an unconditional effect. It's not conditioned on the value of m, or any other variable in the model. There's only one variable in this model in this case. Now that's a bad property if you're interested in moderation, because moderation means the opposite, that a variable's effect is contingent on another variable in the model. Now, if you read ahead, you'll recognize this if you've ever done moderation analysis. Here's how we get to this. Let's let x's effect be a function of m. So what I've done here is I've substituted that partial regression coefficient b1 for some function. And let's just, for simplicity, let's set that function, let's make that function a linear function. We could choose other functions, but linear functions are the most commonly used. So I substitute that function in, and here's what I've got. Now you just rewrite this, do a little algebra, distribute the x among the two terms, and you end up with this. So by letting x's effect be a linear function of m, I end up with a model that looks like this. So by adding the product of x and m as a predictor to this model, we now end up with a model in which x's effect is a linear function of m. The strength of that moderation is going to be determined by the size of B3. So here's an example of how that works. So I've tacked on xm as a new predictor, and I've given it some weight. So here is an example. Same data set. Different estimates, of course, for y because it's a different model now. But look what happens. Now the two cases that differ by a unit on x differ by a different amount on y depending on what value of m you choose, as reflected in the slopes that are not parallel. That divergence from parallel will be determined by the size of B3. So when B3 is 0, so if you set B3 as 0, you go back to this model, one where x's effect is independent of them. Those lines would be parallel. as you deviate from 0, those lines then become non-parallel. The larger B3 is, the less parallel they are. So B3 is important. Here's another way of representing this, and I'll be using this notation throughout the rest of today. So let me go over it. So here's our model with the product of x and m as an additional predictor. We saw that we can rewrite it this way. Right, so I group terms involving x, and then I've isolated x, pull that x out. So that's another representation of that model. Or let's just substitute this thing theta xy into where I set that to this. So that we'll call the conditional effect of x. Theta is the conditional effect of x on y. It's defined by this function, b1 plus b3. So there's a nice way of representing this conceptually, where our focal predictor is x, our moderator is m, and so this effect from of x on y is this function, theta xy, which is b1 plus b3m. So B3 plays an important role in moderation, because if B3 is 0, that basically then that turns this whole function into just B1, where x's effect is no longer dependent on them. It's independent of them. So we test moderation by testing the value of B3 against some alternative. So here's an example. Three variables from our data set, our original data set. I've changed some of my labels around relative to what you'll see later. I'm still calling economic stress x. Now I'm calling depressed affect y. Before we were calling that m. And now I've got another variable I'm calling m. That's the social ties variable. That's the strength of their social networks, business-related social networks. So we want to know, do social ties influence the relationship between stress and depressed affect? So does these social ties, do they somehow buffer or amplify the effect of stress on depression? So here's this model in conceptual form, where my focal predictor is economic stress. That's the variable whose effect I'm interested in quantifying on the outcome y. And then I say, well, that effect is, I believe, maybe moderated by social ties. And then I've got a bunch of covariates that I'm including in here. I did this earlier, so I'm going to stick with that. Here's the model in statistical form. So this is more like what it would look like in the form of a structural equation model, although I've thrown out the error terms, and you often would correlate all these things together if you were drawing it out in AMOS or another program. The important point is that this conceptual model translates into a simple equation. And this is a graphical representation of that equation. And our focus is on B3 at this point. We want to know, is B3 statistically different from 0? That's the product of xm in this model. So here's a simple SPSS code. All I'm doing is I'm creating a new variable I'm calling interact. It's the product of economic stress and social ties. And then I'm including it as a predictive variable in the model, and here's the output that I get. So here's our equation. Here's a graphical representation of that equation. And my regression coefficient, my estimate for that product term is minus 0.212, and it's statistically different from 0. P-value is smaller than it wants to show me. So from that, all we conclude is that the effect of economic stress on depressed affect seems to depend on, or is moderated by, social ties. That's all that we've got from this so far. This is a very abstract mathematical representation of the data. How to make sense of it is anything but clear. We have this estimate. We know it's different from 0, but so what? I mean, what does that mean exactly, except that we now know that this relationship between stress and affect is dependent upon social ties. A picture is always helpful, and I would argue is in fact mandatory. Before you start talking about these things, you really got to draw a picture. Here's a picture of that moderation. So what am I doing here? Well, at the top we see the regression model with those 6 regression coefficients now included. And it's B3 was our product term, the regression coefficient for our product term. Now notice there are 2 terms involving x in this model. So I'm rewriting this equation this way by grouping x and then isolating x. So I'm factoring x out of 2 of the terms. The reason why I do that is because this is that function, what I was calling theta xy. Right? So theta xy, the conditional effect of x on y, is this function b1 plus b3m. Here I plugged in some values of social ties from the data, plug them into this function, and you get theta xy for those different values. And those correspond to the slopes of these lines. So what it seems like is happening is that social ties appear to be buffering the effects of economic stress on depressed affect. People who report relatively few social ties, now 1 is the lowest we get in the data. Remember, these are people who are members of a social networking site. They've all got at least one person in their network. Those people with relatively few ties, the relationship seems to be positive between stress and depression. But among those who have greater ties, now don't think of these in absolute number though. These aren't how many friends you have or something like that. It's actually an index based on frequency of contact with members in the group. But those who have more frequent contacts have stronger ties. The relationship is weaker, if anything, is even 0 and maybe even slightly negative for those who are much higher in their social and stronger and have much stronger social networks. So that's a lot easier to see than trying to interpret that minus 0.212. So a picture is helpful. And this picture allows us to see how these slopes link onto that function, theta xy. We have a number of tools available to us for doing this. One of them being something called the pick-a-point approach, or you might hear this also called the analysis of simple slopes. Same thing, different label. So when we probe an interaction, we're focusing ourselves on picking values of the moderator and then testing a hypothesis about the effect of x on y at those values. So select a value of the moderator at which you'd like to estimate the effect of the focal predictor's effect. Then we'll derive its standard error and proceed as always. We can use that information to test a hypothesis or to generate a confidence interval for the conditional effect, theta xy. Right? We already know how to generate theta xy for any value of m that we choose. We need a standard error, and it turns out that that's not a difficult problem, not even all that difficult to calculate by hand. You get most of the stuff you need from a regression output, standard errors and values of paths. You don't get this thing called the covariance of regression slopes automatically. You'd have to ask for that and then know where to find it. And with any luck, you're plugging in the right things in the right locations, and you get a number that is almost certainly going to be wrong anyway, because rounding error is going to creep in there. You're doing these to 2 or 3 decimal places probably. And that can be significant when you start squaring small numbers and taking square roots. So you could do this by hand. You're likely to make mistakes along the way. There are online tools that do it for you, and Process will also do this for you automatically. So no need to have to go into Aiken and West or Cohen and find those formulas and plug away. There are easier ways of doing it. You'll see an output for that later. I've implemented the pick-a-point approach here, just using those values of m that I chose earlier, calculating the conditional effect of x on y, and then getting a p-value from this method. And that's what you get. So what it looks like is for those who are pretty low in social ties, arbitrarily 1 and 1.5, the relationship between stress and depression is positive. Statistically, it's different from 0, but above, for those other values I chose, 2, 2.5, the relationship is not different from 0. Of course, the problem with this, though, is how do you choose m? Right? I mean, what do we use to guide our decision? How do you know which values of n you choose? And certainly, with the value of n you choose is going to influence the result that you get. And often there's no basis for choosing the moderator, the values of the moderator. Instead, you just rely on convention. And there are conventions out there. The most common is, well, you just choose a mean, maybe the mean of the moderator, and then a standard deviation below and above. Use those as sort of operationalizations of the notion of relatively low, moderate, and relatively high on the moderator. But those are arbitrary, of course. There's nothing magical about those values. You could choose other values. But regardless, you're not going to be able to get around the arbitrariness of the selection most of the time. There might be some reasons, depending on the variable, how you've measured and what your moderator is, there might be some practical or applied meaning to certain values. But most likely, you're going to find yourself in a situation where the decision is arbitrary. There is a better method that gets us around this problem entirely. And that's something called the Johnson-Neiman technique. The Johnson-Neiman technique has been around since around 1937, I think. And it comes out of the analysis of covariance literature. So, you know, when you do an analysis of covariance, you want to compare differences between two groups on some outcome, but you know those groups might differ on some other variable. You want to partial that effect out. Well, analysis of covariance makes this assumption of homogeneity regression. You have to assume the relationship between the covariate and the outcome is the same in the two groups. And what if you violate that assumption? Well, the Johnson-Neiman technique comes out of that. How do you make an inference about differences between groups when you can't meet the homogeneity regression assumption in analysis of covariance? The Johnson-Neiman technique, though, has been generalized to any regression model with interactions. That was done in 2005 or 2006, I believe, by a group at the University of North Carolina. And since then, and since I published some work implementing this in SPSS and SAS in a 2009 paper, it's caught on. And I think that once you learn how easy to learn, first of all, once you come to appreciate it and then see how easy it is to do, this will probably be what you do in the future. And since 2005, 2009, somewhere in that area, we've seen more and more people doing this. Anyway, let me describe it, and then you can get excited about it. I'm already excited about it. Okay, so it really reverses the problem. Whereas with the pick-a-point approach, we have to choose M, and then find out, well, is the conditional effect of X on Y significantly different from 0 at those values? But how do you choose M? Well, let's reverse the problem. Let's find the values of M for which the effect of X on Y is different from 0, and the values for which it's not. Now, it turns out that you don't have to do a whole lot of computation for this. Because you can conceptualize the problem in terms of identifying what's called the regions of significance. That is, mathematically, well, let me show you what we're doing. So here's our conditional effect. We choose some value of M. Right? In the pick-a-point approach, we have to choose a value, and then we generate a standard error for that. And that'll give us some value t, which we then generate a p-value. Now, we don't care so much about t. It's really just a way of getting to the p. The p comes from the t distribution. We don't even really care exactly what the t value is, so long as it's at least some value that gives us a p-value of 0.05 or less, or the so-called critical value of t. So let's reverse the problem and say, well, let's decide what would we like the critical value of t to be. Well, that will depend on the alpha level we choose for the test. It's generally around 2 regardless, but sometimes a little bit less than that, or a little bit more, depending on the sample size. So let's instead say, let's decide what we want our critical t to be, and then figure out what values of M produce a critical t exactly equal to that. Now that's important because those define what are called the regions of significance. Those are points of transition. Think about the moderator's continuum. As you move from left to right on that continuum, you can calculate the conditional effect of X and put a p-value onto it. And as you move left to right, the p-value will change depending on where on M you choose. There will be some point or points at which something is significant at a certain value. As you increase M, it's no longer significant. And then maybe it's not significant anymore for any other value. Or it could be that it's significant, becomes non-significant, but boom, at some value of M changes to significant again. Or it could be that it's not significant out in these streams, but it is in the center. So these points of transition are important because they define the regions of significance. So what we're doing with the Johnson-Neiman technique is we're trying to find the values of m that define those points of transition. Now, when you do some stuff from grade 9 mathematics, grade 9, grade 10, maybe grade 8 if you're advanced, well, in the US, you're probably doing this in 6th grade here. So if you plug in, if you work through this, what you're going to end up with is a quadratic equation. That is, we're going to isolate m. And we set that to 0 when we have something called a quadratic equation, or we use something called the quadratic formula to generate the roots of that quadratic equation. So this will end up with it as a quadratic that has 2 roots. But not all those roots are going to be valuable. Some of them will generate values of m that are outside of the range of the data. Some of them will be imaginary numbers. But there will be some, if they exist, that are within the realm of one's data. So that's all that we're doing. I'll go more into that after lunch for those of you who are hanging around. As I mentioned, this method has become more popular because now it's pretty easy to do in software that you're already using. And a colleague of mine here at Math is now at the University of Vienna wrote this paper where we talk about these methods of probing interactions and provide this tool. ModProbe is that tool, and it is getting quite a bit of use, but Process renders ModProbe obsolete because Process does all this too. So here is, let's go ahead and I'm going to implement this moderation analysis in Process. This is the conceptual model we're estimating. Here is its statistical representation. And here is the process command that does the analysis. Now, as you look through the output, what you will find first is just a standard OLS regression output. So our outcome is depressed affect. It's got 6 predictors. One of them is a product. See here it says that int_1. That's the product term. Notice that I didn't generate that product. There's no product term in this command. It's doing that for you. It knows what to do. It generates the product for you. So this is just standard OLS regression output. You have B1, B2, and B3 in this output, just as you would if you just did this in SPSS, although you'd have to check with the product on your own if you were doing it. And then, Process has a certain intelligence built into it for deciding, absent any other instruction from you, what values of m to choose when it implements the pick-a-point approach. In this case, Process has chosen these 3 values of the moderator, which is social ties, and it's calculated this is theta xy. This is the conditional effect of x on y at those 3 values of social ties. Gives us standard errors, t-values, and p-values, and confidence intervals. In this case, the intelligence that Process has is this. You haven't said anything otherwise, and it sees that your moderator has more than 2 values. So it's assuming, okay, this is a continuum of some kind. And so it will automatically implement the old mean plus and minus 1 standard deviation approach. Absent any other instruction from you, that's what it'll do for a variable that it sees as a continuum. If it sees that it's a dichotomous moderator, that it's only got 2 values in the data, it'll just pick the 2 values because it assumes those define groups of some kind. And you probably want the conditional effect for those 2 groups. So it'll do that. In this case, it goes even further because it chooses 1 for the bottom for social ties. That's actually the reason why it does that. Okay, well, first of all, this is the mean, 1.398. That's the sample mean of social ties. 2.0934 is the standard deviation above the mean. If you're to do the same distance below the mean, you go beyond the range of the data. 1 is the lowest value in the data. So Process knows that, and it picks 1 instead of giving you a number that's actually outside of the range of your data. I don't know how often you've done the pick-a-point approach and ended up in a situation where that low value is outside of your data. It picks that up for you and doesn't let you make that mistake. Okay, so that's the pick-a-point approach, and it does that for you whether you want it or not. You can't stop it. But what is an option is the Johnson-Neiman technique. You have to ask for that, but it's a simple 4 characters in the code. And this is the output that you get. So what it's telling us is it finds two values that identify the regions of significance of the effect of x on y. Those values are here, 1.89 and 2.81. That in itself is not very helpful, though we need more information than that. So it generates this table where it slices the distribution up into 21 values. It gives you the values of the moderator, calculates the conditional effect at all those values, brings in the values of the moderator into that table that it identifies as the regions of significance. And from this, you look at the p-values. And the point of this is not to interpret each of these as a literal hypothesis test. The point of these is to see what's happening at the point of transition. Notice here's one of the points of transition, 2.81. See the p-value is exactly 0.05. Everywhere above that, it's statistically significant. Again, at 1.89, that's another point of transition that it found. The p-value is 0.05. And everywhere below that value of the moderator, it's also significant. But anywhere between those two values, you see it's the effect of x and y is not significant.
In the social types, the 21 values that you create, are they directly from the data, or are they just taking the range and dividing it by
just arbitrarily slicing it up in that way? They're not actual groups, they're not actual values. Okay. You may not have anyone in the data file with those values. Yeah, this is really more, it would be nice to have a picture, and a picture I'll show you. It would be nice to do that, but getting SPSS to do the picture I'm about to show you automatically is quite difficult. It's easy to do it once you know how to do it, but to write the code to do it automatically, which would be relatively error-free, and it won't create a lot of email for me. That's hard. So this is my alternative. It creates a sort of tabular representation of a figure like this. So this is a plot of the regions of significance. So normally you see this would be like an outcome variable, like y, but no, this is an effect. This is theta xy here on the y-axis. Here's our moderator. The red line is that function, theta xy. And then I've placed confidence bands. I don't know how well you can see it with the gray, but 1.893, there's a line going up there, and then 2.80, there's a line going up there. And what you should notice is that the confidence interval includes 0 between those two values. That is the confidence interval for theta xy. For values of social ties between those, the confidence interval includes 0. For values to the left of that 1.89, the confidence interval is entirely above 0. So 0 is here. And for values to the right of 2.8, the confidence interval is actually entirely below 0. Now, there's almost no one in the data this high. So I really wouldn't interpret this as a negative association. That's personally because I know the data. There's really not enough data up here to make much of this. There's plenty of data down here, though. So what I see happening here is that among those who are relatively less connected in the business community, they're feeling these positive effects of stress. The people who are more connected aren't. Okay, so that's pretty neat. It allows us to wash our hands entirely of the arbitrariness of the choice of them. Instead, we just analytically figure out what are those regions of significance. As you'll see after lunch, it may be that there are no regions of significance, or no points of transition, and there are a number of possible things that can occur to make no points of transition. All right, so now here we are finally, where things get exciting, and as I promised, I start running out of time, and I certainly want to leave some time to take your questions. Okay, so combining moderation and mediation analysis, what I call conditional process modeling. We've essentially, all we're doing is we're merging two concepts. Process analysis, or mediation analysis, same thing. Analysis was the original term from the early 80s. And moderation analysis, the notion of interaction. We're putting these two things together to model the contingent nature of mechanisms. If indirect effects quantify mechanisms, and interactions quantify contingencies, combining them allow us to model the contingencies of mechanisms. That's all that we're going to do. People have been talking about this for a while. I'm certainly not the first, although I am the first to use the term conditional process modeling. People have been talking about this for quite some time. Maybe I shouldn't, depends on your perception of history. Actually, it hasn't been that long. It's been 8 or 9 years now. But it's been around before then. I mean, it was the 80s sometime people started talking about this, but nobody really was very systematic about it until around 2005. And then there were a bunch of people doing this, myself included. And here we are today, conditional process modeling. Here's the gist of it. So we know that in a model like this, we can quantify the indirect effect. It's a product of two paths. But what if the path from x to m is moderated? So maybe that path is moderated. Or perhaps that path is moderated. Or both. It could be that you have both of those paths moderated. If that's the case, then that means, because we saw earlier in those situations that x's effect on m is a function. It's a function of w. Or m's effect on y might be a function of z. That means that our indirect effect is no longer just a single number. It's instead a function. It's a function of moderators. In other words, the magnitude of the indirect effect will depend on at least one other variable in a model like this, in this case 2, or what we call moderated mediation. So the mediation, the indirect effect, is moderated. And in that situation, then it becomes sensible to ask, okay, so what is the value of the indirect effect conditioned on a value of the moderator, or what we call conditional indirect effects? How do you quantify those? How do you make inferences about them? Direct effects could also be conditional. You could have a situation in which the effect of x on y independent of m is itself moderated. Here are some of the possibilities. And this is just a very, very small sampling of the possibilities. You can imagine this is just with a very simple mediation component, a simple triangle with one variable. Yes, people are doing this. Here are a few examples. Examples in which the x to m path is moderated by w, something called first stage moderated mediation. That is the first stage of the mediation component moderated. Here are two examples of what we call second stage moderation, in which the path from m to y is moderated. Right, so let's go back to our example. Here's the model that I started with. I said, here's where we're working towards. Well, here we are. This is the model that I've showed you at the beginning of this talk. It's a conditional process model. It proposes the indirect effect of economic stress on withdrawal intentions due to depressed affect is modeled. It's moderated at the first stage by social ties. But we're not allowing the direct effect of stress on withdrawal intentions to be moderated. That's a decision that we're making in the modeling phase. Okay, so here's that conceptual model. Here is its translation into statistical form. Now, making that link from conceptual to statistical is probably the hardest part of learning this. How do I take my conceptual model and turn it into a set of equations in that case? But this is the model in statistical form. So it's represented with two equations, because we have two outcomes, really. We have the outcome here as a mediator, and we have an outcome here as withdrawal intention. So we have two equations. Let's break this up so you can see where this is all coming from. Okay, so here's our conceptual model. We have a component of this model is a moderation component, right, where we have x's effect on m moderated by w. So think of that as just a moderation model, and it's got a couple of controls, because there are these control variables in the model of m. So that's this part of this equation. Our moderation component is this. And we got the stuff we're parceling out for good measure. So this part of the conceptual model translates into this part of the statistical model, in this part of the equation for m. See that? Now notice, although when you look at this, you might think, okay, well that's A1. Well, no, it's not. It's not A1. Because remember, this path is a function of W. It's shown by grouping the terms involving x and isolating x, right? So that is actually that A1 plus A3 W in this model. Right? So another way of writing this part of the model is like this, where I've just substituted theta xm, where I define that as this function of W. Does that make sense? Okay, well, what about this component? Now, our mediation component, then we have this effect of M on Y, and then we have the direct component. Well, that's down here. Then we got the covariates. That corresponds to the parts in red of the statistical model. M's effect on Y holding everything else constant, in this case, is V1. It's not moderated, it's not a function. Okay, so that allows us then to talk about the notion of a conditional indirect effect. So it's this function here. V1, that is the effect of M on Y. There's no moderation there. So the indirect effect of X on Y through M isn't A1, V1. It's this function theta xm times V1. Doing all the substitution and expressing it purely in the form of variables and coefficients, that's the indirect effect of X on Y through M. It depends on W. So that's our conditional effect of X. I'm sorry, our conditional indirect effect of X on Y through M. This model has a direct effect, and it's not moderated. It's merely the effect of X on Y independent of M, and that's just C prime. Okay, so now you've seen how that all works without the numbers. Now let's just put the numbers in from the analysis itself. A1 and A3, we've already done this. We did this earlier in the moderation component of this talk, but I'm just repeating it here. This is the same model we used for when we were modeling the moderation of the effect of stress on depressed affect. We've seen this output before. We've seen A1 and A3, although we called them V1 and V3 before. There's our minus 0.212 that you saw earlier. You've got to bring in the coefficient for X into that as well. So A1 and A3 are those two values. B1 is simple. We've seen this before too. There's the 0.707 that we saw from the simple mediation analysis. And now we've got everything we need. Right? We needed A1, we needed A3, and we needed B1. So put those together. So the conditional indirect effect of X on Y through M is the product of the conditional effect of X on M, that's A1 plus A3W, and the effect of M on Y, that's B1. So there it is, in generic form, and now it's with the numbers from the regression analysis brought in. Now we can proceed much like with the pick-a-point approach, right? Let's just choose some values of W, our moderator, and figure out what the conditional indirect effect of X on Y through M is for those values of W. So here I just arbitrarily chose some social values of the moderator, social ties. We know that different values will produce a different effect of stress on depressed affect. So that depends on social ties. The effect of depression on withdrawal intentions does not depend on social ties, at least not in our model. That's not to say that it doesn't, but we haven't modeled it in a way that allows it to. Those two numbers, when multiplied together, give us then the conditional indirect effect of stress on withdrawal intentions through depressed affect. It depends on social ties. So it seems that that indirect effect is decreasing with increasing social ties. Now these are just descriptions, mathematical descriptions of point estimates. We would like to do an inference as well. Just like in the pick a point approach, we can estimate a conditional effect and then conduct an inference about it. The same thing here. We can estimate the conditional indirect effect and then make an inference about it. And bootstrap confidence intervals are great for this. Because again, notice this is the product. This involves products of normally distributed regression coefficients. It's not as obvious here, but there are products of regression coefficients involved here. So that's going to have a fairly irregular sampling distribution. And so a method like a bootstrap confidence interval would be a great inferential tool for that. I'll get to that in a second. Let's talk about estimating the direct effect. There's nothing really to talk about, fortunately. It comes right out of that model for y. It's just that C prime path, and that's minus 0.094. And that is not statistically different from 0. You've seen that before. We started the talk with that. Here's a visual representation of the direct and the indirect effects in this model. And what I've done here is the line is the effect. And I put social ties on the bottom. That's the moderator. Here's the effect. And it's either a direct or an indirect effect, depending on the color. So the gray is the direct effect, and then I've added the endpoints of a confidence interval. And that's not a function of W in my model, so that's the same anywhere you pick for the social ties. The estimate is minus 0.094, where the confidence interval includes 0 regardless of the value of W. For these relatively low values of social ties, a bootstrap confidence interval does not include 0. It's positive. But for these more moderate or higher values of social ties, both the direct and the conditional indirect effects are not different from 0. So the mechanism at work here, depressed affect, seems to be operating primarily for people with relatively few social ties. No evidence of a direct effect elsewhere. No evidence of a direct effect anywhere. No evidence of an indirect effect anywhere except among those with relatively few social ties. Now, where do those endpoints come from? Well, I talked about bootstrapping. This is a 2009, it's a 2007 paper that I tagged on with Chris and a colleague at the business school at Northwestern, Derek Rucker, where we introduced these ideas of conditional indirect effects, and we talk about different inferential methods for them. We talk about a normal theory or Sobel-like approach to this, which I don't recommend. We also derived the Johnson-Neiman results for conditional indirect effects, which seems like a natural extension. But I actually don't think that was such a good idea anymore. And I think Chris and I are in agreement on that. Sometimes you have a good idea and you can even convince people it's a good idea. And then you realize later, oh, maybe not. So I don't really recommend this because it does invoke this assumption of normality. The derivation of the regions of significance for conditional indirect effects does invoke this assumption of normality of the sampling distribution. So I'm not so comfortable with that. So bootstrap confidence intervals is what I prefer. But process does all the stuff that this tool that we describe in this article also does, ModMed. So ModMed isn't even useful anymore because process does everything ModMed does, except for the Johnson-Neiman stuff, which I don't recommend. So here is this model implemented in process. So here's our conceptual model, here's our statistical model, here's the code that generates the output that we've got in front of you. So here what you'll see is our model of depressed affect. This is just standard loss regression output. There's our coefficients, A1, A3, and A2. We don't even need A2, but there it is. So there's A1 and A3. Here's our, notice that process has generated that product for us. It's done it for us automatically. We didn't have to do that. It knows when I specified model 7 that involves this product term that's needed. And so there's our outcome of withdrawal. That doesn't have a product in it. It's not needed. There's B1. There's C prime. Then it gives us this summary. And again, it knows what this model looks like. It knows there's an unmoderated direct effect. So we just get that in the summary. There's that minus 0.094. And then it knows the conditional indirect effect is a function. So it's chosen arbitrarily values of the moderator and calculated the conditional indirect effect, the conditional indirect effect with those values of the moderator, and then generated bootstrap confidence intervals. So the endpoints for this figure I generated, actually not with that command. There's an option in process that says it allows you to specify the value of the moderator, and then it'll generate whatever you want for that value. And so I used process to generate the endpoints from that figure here. Okay? The last thing I want to talk about, and I'm only going to give you a hint of this. If you're going to be with me at the end of the day tomorrow, you'll get more details. This is my next work. A work in progress. The paper on this is about a third of the way through, but I'll give you a preview. Here's the issue. We have not really formally tested for evidence of moderated mediation. We've done through a sort of a piecemeal approach. A logical argument says that, well, if one of those paths is moderated, then so too, therefore, must the indirect effect be moderated. But it's possible to be more formal than that. And it relies on this insight. We can think about mediation being moderated if the size of the indirect effect depends on a moderator. So that pattern of results implies moderated mediation. We've seen evidence of moderation of one of the paths, and we've seen that for some values of the moderator, we have evidence of an indirect effect that's different from 0, but not for other values of the moderator. But we haven't formally tested whether the indirect effect is moderated. We tested whether one of the paths is moderated. But the indirect effect is not that one path. It's the product of paths. But look at this. This line is that function, right? So the conditional indirect effect for this model is a line. Let's make that clear just by rewriting this in this form. So I've just taken the V1, distributed among the terms, plugged in the coefficients, and that's the equation for this line. So the slope of this line is minus 0.150. The question is that slope statistically different from 0? That becomes a formal test of moderation of the indirect effect. Process does this for you. Well, it can give you the information you need, and then you have to take it one step further with the process, with the information process gives you to do this test. And I will show you how to do that with one example toward the end of the day tomorrow. Otherwise, there's a paper coming out on this topic. All right, so here's where we've been. So all effects function through some kind of a mechanism. I think we can all probably agree that that's true. Effects don't just magically come to be. There's some kind of mechanism at work. And mediation analysis has changed since 1986. We're not doing things Baron-Kenny style anymore, although I haven't told you why that is. All effects are contingent on something. I think we can probably all agree that's true too, although we don't always model the effects as contingent. Probably there's contingencies that we haven't modeled that are there. And if that's true, then any analysis which focuses only on one or the other but not both is going to be incomplete in some way. We can combine moderation and mediation analytically together, and we can do this in so-called modern ways, and it can be done fairly easily on software that you're already using. If you want to learn more about this, I have a homepage which has links to all my work on this topic, as well as all of the statistical tools that I've written over the years. You'll also find process there. If you want you've received the fast version of this material. If you want the slow motion version, you can take a whole class from me in the summer. I'm teaching the 5-day course on moderation mediation analysis with Chris Preacher in Philadelphia, and that's July 15th to the 19th. I've hidden from you the price there, but it's going to set you back about $1,700. I'm not sure I'm worth that much, but fortunately I don't get even much of it except a small chunk of that. So, but it's where we go into all kinds of detail, all kinds of different models, all kinds of fun stuff that you can do with this. And then finally, I have a book coming out on the topic, which was mentioned in my introduction. And this is where you can learn more about both moderation, mediation, and conditional process modeling in one place. hear the things that people will say about this book if you give them a free copy. And you can actually get this book now, although it's not available until June. You can order it through their website or even through Amazon or other places. So go ahead and spend your money now if you want, but wait until summer before you get it. I appreciate your attention and have fun. Get some sleep. Don't lose sleep using process. I think you might if you let yourself. And as always, I try to take emails from people. I get a lot of email. I always give priority to people who have attended my talks or my workshops. So if you have a question for me, identify yourself. Say you came to this, and I will put you higher in the list. Okay?